bell for the end of the school day may have rung, but the learning doesn't end there. This is your geography revision session. We're covering Year 9, Module 1, The Restless Earth. I'm Mr. S and I'll be your revision tutor. The Restless Earth module is all about tectonics. This is the movement of huge slabs of rock, which we call plates, and their interactions which produce both landforms and hazards. As always, we have 5 elements to look at, so let's start with the structure of the Earth. Now there are 2 things that we're going to look at in the structure of the Earth. First of all, the layers that make up our planet, and then the different types of crust that we get on the outer layer. Let's start with those layers. And at the very centre of our Earth, we have what's called the inner core. And that's made up of a solid sphere of nickel iron metal. It's solid because it's been compressed by all of that force pressing down from the upper layers of our planet. And it's so hot down there that it's producing all the heat that's keeping our planet warm. It's around 6,000 degrees Celsius in the centre. As we move out from the inner core, we come to the outer core. And here, we've still got metal made up of nickel iron. However, it doesn't have as much pressure pushing down on it, and it's now in liquid form. So there's metal in a purely liquid form. And it's not quite as hot out in this layer because we don't have, again, as much pressure pushing down, and therefore it's 4,500 degrees, but still a very, very warm temperature. Next up, we have the mantle. And the mantle is made up of molten rock. It can flow like a liquid and moves in what are called convection currents, which you may have studied in science, where we have a liquid which is heated up from the core, and as it's heated it will rise up because a heated liquid becomes less dense. The particles that make it up are spread further apart and therefore will move up away from the more dense material until it reaches the outer edge of our next layer, at which point it will move along that edge until it cools, and as it cools it becomes more dense, and as it becomes more dense it will sink back down towards the core, and that will go around in a cycle which is called a convection current. And that's important for something that's going to come up later on. Now this is our biggest layer as well, our thickest layer. It's nearly 3,000 kilometers thick. And then at the top we have our thinnest layer, and this is called the crust. And the crust is what we're standing on now. It is a broken part of the Earth, and by that I mean it's split up into lots of little bits which we call plates. And there are 2 types of plates, one called oceanic and one called continental, and they float on top of the magma inside the mantle. And this is where the convection currents come into play. As those convection currents move along the underside of the crust, along the underside of the plate, it pulls or moves those plates in the direction that it's moving. So in this case here, the convection current is moving in this direction, and it's moving this plate that way. This convection current is moving this way, and it's moving this plate that way. Now, as I said, there were 2 different types of plates that we need to consider. We have oceanic and we have continental. Oceanic plates are the ones that we've typically found, obviously, underneath the ocean. They are a lot heavier and a lot thinner than continental plates. And the reason for that is because we've got all this water above it. Any sediment or any dead animals over time will fall to the bottom, and the force, the pressure of that water is going to push it down into the ground, into the plate. And if you imagine that's going on for millions and millions of years, it's going to compress a lot of material down. It's going to remove any air pockets and become really, really thin but really dense. They pack together. Whereas on the continental plate, it doesn't have anything other than air pressure pushing down on it. And therefore, it hasn't built up as much in terms of how dense it is. There's still going to be large air pockets in there, and it means that when it does build up, it allows it to become much thicker. So that's lighter, but it is a lot thicker. Now there are other unique elements about both of these plates. Oceanic crust can be destroyed and it can be made. And the reason for that is that because it's denser, it can be forced underneath the continental plate. It goes underneath because it's heavier. And when it does, it's going to go down into the mantle. Well, the mantle is really hot and it'll melt this plate, so it gets destroyed. But in another location where there's a gap, magma will rise up and it'll solidify, so it becomes solid and becomes new plate. It becomes new oceanic plate. Whereas continental plate, it's so light that it just rests on top and it doesn't sink, so it can't be destroyed and it can't be remade. And it's the continental plate that we're stood on. Next up, let's have a look at some of these interactions between these two different types of plates. And this is called plate margins or plate boundaries. And there are three that we're going to consider. We have a constructive plate margin. So just as I was saying that oceanic plate can be made, this is where oceanic plate comes from. As these convection currents are moving away from each other, this part of the plate here is going to move to the left and this part of the plate is going to move to the right. Well, that produces a gap down the middle. And that means that magma from the mantle can rise up. And as it does, it's going to start to cool because it's getting further and further away from the centre of the earth. And it's going to get very close to the water from the ocean. So as it cools, it's going to solidify, so become solid on the sides of these plates. So this here is brand new oceanic crust. And the further away we get from this gap, the older that rock becomes on both sides. So as the plate moves, more magma rises up, cools and sticks to the sides of the plate and creates new land. Now there are other things that are happening here. When magma rises up to the surface, that's called a volcano. And that's what's happening here. So at constructive margins we get volcanoes, but they tend to be underneath the ocean, which we call submarine volcanoes. And there's also another little thing happening here as well. So at the side of the volcano, this sort of lip, this ridge that comes up at the side, and that goes all the way along this gap in the plate, and that's called a mid-oceanic ridge. And there's a big example of that in the Atlantic Ocean, called which goes right the way from Iceland down through the Atlantic Ocean across the equator. Our second one is a destructive plate margin. And again, we've already kind of discussed this, where we're talking about oceanic crust being destroyed. So you can see here that this convection current is moving the plate towards the continental crust, which is coming in the opposite direction. And it has to be the oceanic crust that sinks, because the continental crust is lighter, and so it floats on top. And this one is heavier, so it gets pushed down. So as it gets pushed down, that plate goes into the mantle and melts. It's being destroyed. And there are two things that are happening here. When these two plates collide, it's not smooth, so they're not just going to glide past each other, they're rough, it's rock. And so it's going to snag, it's going to get caught, and over time pressure is going to build up as this one's moving this way and this one's moving this way, until the pressure is overcome and it suddenly jerks past each other. That friction, when it's released, is going to produce an earthquake. And then secondly, when this plate is going down into the mantle, it's melting and it's producing more magma, which needs to go somewhere. So the magma starts to force its way up through the plate. So this can happen on the oceanic side or on the continental side. And it'll rise up, finding weaknesses in the rock or gaps from those air pockets until it reaches through to the surface and creates a volcano. So at destructive margins, we get both earthquakes and volcanoes occurring. And again, there are other features that we can consider. This point here, where we've got the continental plate and the oceanic plate coming together, that isn't just a flat point. It actually goes down really deep, and it produces some of the deepest points on our planet. And these are called deep ocean trenches. Very, very deep gaps between the oceanic plate and the continental plate. And an example of that is the Marianas Trench in the Pacific, the deepest point on our planet. The second one is a fold mountain. And a fold mountain is formed because as these two plates collide, the continental plate can't go anywhere. And what happens is it starts to bend and push itself upwards. So this here would have been a lot flatter, but as it's pushed into this plate, it's pushed itself further up into this mountain shape. And anything caught in between the oceanic plate and the continental plate, such as sediment from the top of the ocean on here, is also going to get pushed up and folded into this mountain as well. And then finally, we have conservative mountain margins. So we've got a pattern going on here. Constructive is creating land. Destructive is destroying land. Conservative means that nothing is gained and nothing is lost. In this case, these plates are moving in similar directions. So we're not going to lose any land, we're not going to gain any land in this case. Now, this is a picture of the San Andreas Fault, which is in Western America, a lot near like LA and San Francisco. And you can see that one plate's moving in a slightly different direction, but generally they're moving in the same way. And you can imagine, as these two plates are sliding past each other constantly at different rates of movement, but also at slightly different directions, that there's going to be a lot of friction that builds up here, and therefore we're also going to get a lot of earthquakes occurring as well. But nothing is being lost because neither of these plates is subducting, going under, and nothing is being gained because there's no gap being produced between the plates. These plates could also be going in opposite directions, so we could change this arrowhead from this side to this side and it would still be a conservative plate. They're just moving in opposite directions as opposed to similar directions. Next, let's have a look at some of these hazards. And the first one we're going to look at are volcanoes. And there are two different types of volcanoes, and which one happens depends on what margin it's being produced at. So there are shield volcanoes and stratovolcanoes. A shield volcano is produced at a constructive margin. That's where the two plates are moving away from each other. And the reason for that is it creates something called basic or basaltic lava. And this lava is really runny and really thin. And that's important because as this rises to the surface, this lava is going to run quite far away from the vent where that magma is coming out. And it runs really, really far away. This means that the layers of lava that build up are going to be really thin. And this means that our base is going to be really wide because the lava is traveling a great distance, but it's not going to grow very tall because all these layers are really, really thin. And in reality, there aren't really layers because it's just lava that's building up over time. So you've got low profile, not very high, wide base because the lava runs a great distance away from the vent. It's made up of runny lava, it's made up of only lava, there's no ash really. And these types of eruptions occur really, really frequently, but they're not very violent. By that I mean that in some cases like Hawaii, some of these shield volcanoes are constantly erupting, but because it's only made up of runny lava, there's no build-up of energy or pressure to create a really violent eruption. So it's kind of just a gentle flow of lava constantly. And in contrast, we have stratovolcanoes. These are the shape of volcanoes. If I asked you to draw a volcano, a lot of people would draw a big triangle like a mountain. And that's essentially what a stratovolcano is. And we characterize these by having a very narrow base. So they're not as wide as a shield volcano, but they are really, really tall. And they're made up of something called andesitic or rhyolitic lava. This is really, really thick lava. It's made up of molten rock, but it's got a lot of something called silica in it, which makes it really thick, really sticky, and it doesn't flow very fast. And that's important because it means that the lava is not going to travel a great deal away from the vent. And it's also going to produce a lot of ash. And that ash is going to lie on the side of the volcano along with the lava and produce these really thick layers, which mean that it builds up to be really tall. But because it doesn't travel very far away from the volcano, the base is really narrow. So you've got a high profile, how tall it is. It's a very narrow volcano, and it's got thick lava and thick layers. And it's made up mainly of the ash that's produced by the lava in these layers. And this occurs at a destructive boundary. So this is the lava, or the magma in this case, being pushed up to the surface, but it's gaining more silica, making it thicker because this plate is melting and putting it into the magma here. And this erupts very infrequently. So in some cases, it can be thousands and thousands of years between eruptions. And the reason for that is this really thick andesitic or rhyolitic lava takes a long time to build up and a long time to be put up and pressured through the vent. So these can build up and cause blockages that have to build up lots of pressure to release. And that build up and that release is what creates these violent eruptions and lots of ash. Next, let's consider earthquakes. Now we know that earthquakes can form at two locations. They can happen at destructive boundaries and they can also happen at conservative boundaries. And they happen because of the interaction between two plates, the friction as they try to move past each other. And there are a few key points that we need to understand around earthquakes. We can talk about where an earthquake happens as either the epicenter or the focus. Now the focus is right down inside the plate where that friction is first built up. So in this case it might be down here or down here. That's the focus, exactly where the earthquake happened. But that's not really useful to us as humans because we don't live down where the focus is. We live on the surface of the planet. So we need to be able to locate where that is happening on the surface. So that's what we call the epicenter. That's the point on the surface of the planet. So that would be here on this one, or here on this one, where the earthquake happened, where we're standing. And that's more useful for us because it can say, well, it's right inside the city or it's just outside the city, for example. And then we also have something called the fault. And the fault is easiest to see on this one. It's the dotted line. So the fault is the line where the two plates meet. And it's the place where those earthquakes will be happening along. And then we've got seismic waves. So seismic waves are the energy that is released when these two plates overcome their stress, their friction. And when that occurs, the plate will move a quick jolt, releasing all that pressure, and it's released as a series of waves, which we call seismic waves. And they're represented here as these red circular lines. And they travel through the ground, and when they interact with the ground, they shake and can produce all sorts in terms of different types of damages, which you'll have studied in class. And finally, we have tsunamis. Now, tsunamis are unique in the sense that they aren't actually a primary hazard. They are formed by another hazard that occurs first. In this case, it's an earthquake that has to happen below the surface of the ocean. So let's have a look at this in a bit of detail. This is also going to help explain earthquakes in a bit more detail as well. So you can see here that we've got two plates that are forcing against each other, and this blue area here represents the pressure, the friction that's building up over time. As that pressure becomes so much that it overcomes its inertia, its pause, it's going to push in one direction. So in this case, it's been jolted in this direction, and that's moved up. So that's releasing the pressure in that direction. And that's produced a series of seismic waves that are going to radiate out in all directions away from that point of pressure, that point of friction. That's going to create ground shaking, ground motion. And you can see here, that's where it was, so that's inside the rock, so that's the focus, and then directly above it on the land is where the epicenter is. Over time, it'll settle into a new position, but as it's settling between the two, we do get aftershocks, so smaller earthquakes that occur as the land is settling into a new position. But when all of this is occurring underneath the ocean, and that motion jerks upwards, there's a whole host of water above it as well. So as this plate is jerked upwards, it's pushing a column of water upwards as well. And that water column will irradiate out in all directions. So it's not just going to travel left or right, it's going to travel in all directions until it reaches land. So when this happens underwater, the column of water is uplifted and a huge tsunami wave which flows in all directions travels until it reaches the land. And that will continue to travel until it reaches land. and in some cases will travel thousands and thousands of kilometres, such as in 2004 in the Boxing Day tsunami. That tsunami wave travelled and hit not just Asia, but travelled across the ocean and also managed to hit Africa as well. Now, because of the type of plate and the motion that's required, this is produced by destructive plate margins, when you've got one plate colliding with another. It can also be created in other ways as well, though. It can be volcanoes, so this can occur due to submarine volcanoes when they put out an eruption and they force a column of water up as well. And they can also happen because of landslides, which also tend to happen because of volcanoes. So if you imagine on this diagram here, a volcano erupting, it sends some rocks down into the ocean, and that creates a wave that travels away from that point. But the primary way that we would consider is by an earthquake that occurs underneath the ocean. That's it for today, but don't forget to complete the home study questions to test yourself. Goodbye.